The last concept we are going to take a look at in this chapter is what's known as enthalpy change. What is enthalpy? Enthalpy is the amount of thermal energy, which we call heat, that flows through a process at constant pressure. So basically, when we're talking about enthalpy, we're talking about heat. And all chemical reactions either give off heat, which means they're exothermic, or they absorb heat, which means they're endothermic. And the symbol we use to describe enthalpy change is this capital Greek letter delta and capital H, and then we just put RXN down here as a subscript to indicate we're talking about a specific reaction. So we haven't really had to deal with signs very much in this class at all, except for when we were talking about temperature. Then we dealt with signs, negative temperatures. In enthalpy, the sign is very important, and it tells us the direction the heat is flowing. It is negative when a reaction is exothermic. Thermal energy or heat is produced by the reaction and leaves the chemicals. Therefore, the surroundings get hotter, and delta H is negative. So here's an example of natural gas combusting. And we know that when any hydrocarbon or compound made up of carbon and hydrogen combust, heat is always given off. So if we look at this reaction, 1 mole of methane reacting with 2 moles of oxygen to give us 2 moles of carbon dioxide and liquid water, the delta H for this reaction, or the enthalpy, is negative 802.3 kilojoules per mole of methane. So this negative means it's an exothermic reaction. Heat is released or given off, and this is a lot of heat. So this is why we use hydrocarbons such as methane and propane to give us heat when they burn. If a reaction is endothermic, the sign of the enthalpy is positive. So this happens when a chemical reaction needs to absorb heat from its surroundings to occur. And here's an example of that. Here's 1 mole of nitrogen, which reacts with 1 mole of oxygen to form 2 moles of nitrogen monoxide. This reaction requires the absorption of 182.6 kilojoules per each mole of nitrogen. In this case, the surroundings get colder and delta H is positive. Most chemical reactions are exothermic. There are a few chemical reactions that are endothermic, but most give off heat to go to more stable chemicals. Now, we looked earlier at the relationship, or the difference really, between heat and temperature. And one of the differences is temperature does not depend on amount, whereas heat does. So remember, a 5-pound baby has the same normal body temperature as a 500-pound sumo wrestler. But the amount of heat a baby gives off is very different than the amount of heat a 500-pound sumo wrestler is going to give off. So the amount of energy change in a reaction depends on the amount of reactants. For example, we get twice as much heat when we burn twice as much methane. The amount of heat that is absorbed or released is related to the stoichiometry. So let's look at this reaction right here. Here we have, and let's just get rid of this, make it easier to see. This is propane, and when propane is combusted, each mole of propane requires 5 moles of oxygen. It in turn, when this burns, produces 3 moles of carbon dioxide for each mole of propane and 4 moles of gaseous water for each mole of propane, and 2,044 kilojoules of heat are released for each mole of propane. So we're used to, by now, looking at these stoichiometric relationships between our chemicals. We can also apply these to the heat that is released or absorbed in a reaction. So let's look at how we can solve a problem. How much heat is associated with the complete combustion of 11.8 times 10 to the 3 grams of propane? So let's go back to our balanced equation here. Here is our balanced equation, and this is what we'll use to get the relationships we need to solve this problem. Okay, so here's our balanced equation, and part of the equation is 2,044 kilojoules of heat are released when 1 mole of propane is combusted. So I'm given grams and I want amount of heat. Now this is going to be a stoichiometry problem. I need to use my relationship here that 1 mole of propane is going to give me 2,044 kilojoules of heat. This is my relationship that I get from my balanced equation. But if I look at my given, this is in grams. So I've got to get my grams to moles so I can use my stoichiometric relationship. So I'm going to calculate the molar mass of propane by taking the mass of carbon, which is 12.01, multiplying that by 3, and then taking my molar mass of hydrogen, which is 1.01, multiplying that by 8, and then adding the two values. And I get 44.11 grams. Whoops. Okay, so now we can do our railroad math. And if we look at our units, I have 2 of everything. I have grams of propane, moles of propane, kilojoules, kilojoules. So we start with what we're given, 11.8 times 10 to the 3 grams of C3H8. I have grams of C3H8 here. I must have grams of C3H8 down there, so I use this conversion factor, my molar mass, to get from mass to moles. Now my units are moles of propane. I want kilojoules, my final answer. Here's my conversion factor, and this came from my balanced equation. My moles of propane cancel out, and the answer my calculator gives me is 5.46796 times 10 to the 5th kilojoules. Now let's look at my sig figs. I'm given 3 sig figs to begin with. That's my last allowable sig fig, 5.47 times 10 to the 5th kilojoules. Now I forgot one thing here. It's my negative sign, and that lets me know that this is an exothermic reaction and heat is released. Now sometimes the question will say how much heat is released, but this says how much heat is associated. So therefore we definitely want to put our negative sign in there to show that heat is being given off in this reaction.